Okay, what I'd like you guys to do is enter the data that you guys have here, and then we'll let me see if I can find them on either Google Sheets or Excel. Either one will be fine. Okay, let me know when you guys have the data. See how rusty I am. Okay. Okay, you got all three data points. Sure, I have the right one. Okay. Okay, so what you're going to do, you want to graphically do the representation of the graph. Now, we know that if it's a first order reaction, right, then it's gonna, let's see, let's do it. We'll write out our equations. That's the best way of doing it. So what is the equation for the time if it's a first order reaction? You guys recall? Well, we'll start with a zero order reaction. So if it's a zero order reaction, then the equation is going to look like what? The okay, zero order. So if it's a zero order reaction, you guys recall? So you got to speak up because I could hardly hear you. It's been a long week. Okay. Okay. Let's see. Anything today? Wait 1 second. No. This is all screwed up. 1, 2, 3. Okay. First order reaction.
I mean, A of P over A naught equals -2.
Or we could also write it as A naught minus, I'm sorry, A T minus A naught ln A naught obviously this little bug is really interested in chemistry minus KT. Because we know that if we had the natural log of A naught over AT, then we take the minus of that, then the number of the equation. So, okay, so that's the first order reaction. And then a second order reaction. It's going to be you said AT, 1 over AT minus 1 over A naught equals KT. Okay, so if you look at the way this is organized, it's kind of organized very, very similarly, right? Kind of the line, the equation of a line, right? So like here, this is clearly where this here represents our Y. This here is going to represent our X, and this is going to represent our N. And this represents B. We just kind of move things around. Okay, so we're going to kind of take advantage of that to kind of help us figure out whether or not our equations is a first order reaction, second order reaction, or a, sorry, zero order, first order, or second order. Okay, so the way that we would go about doing that is, find the data again. So this is the concentration, and what we would do is just plot it, right? Because if it's a zero order reaction, it's going to look just like a line without having to modify the concentration value. So all you're going to do is going to hit maybe insert your chart. Okay, so when you choose your chart, you're going to choose a scatter plot. And let me move all of this out of the way. Let's see inside here. Okay. So then we're gonna up here and you see where it says add elements. And I'll show you how to do it using Google Docs here in a second as well too. Maybe if my computer decides it wants to behave. Okay, so you're going to go down to Trendlines. We expect it to be linear. If it's going to be linear, it'll fit. So, and then go back down to Trendlines, more trend options. So this window is going to pop up on the side. You're going to hit linear. If you thought it was going to be logarithmic. Oh, we can't calculate a zero value. It's logarithmic. Okay, and then we're going to go down here and we're going to hit display equation. And you're also going to display the R value. Now, this R squared value lets us know how accurate our line fits the curve. If that R value is very, very close to 1, then it's dead on. If it's like 0.5 or something like that, then it's like you want to try again, right? So it really doesn't fit the curve, okay? And then in this case, this guy is really almost on 1, right? We also only have 3 points, so it doesn't make it too difficult. So based upon this, would you say that this is since it fits so perfectly, you'd say that this is a zero order reaction, right? So then that means our equation for our rate is going to be rate equals K, our initial concentration, K naught, right? And that's all the rate is going to be, okay? So in that case, this here is going to represent R minus K. So then K is going to equal 0.013. Okay. A naught. What was that? No, it wouldn't be negative K because the equation is AT minus A naught equals negative K, right? So the negative is already there. The negative is there. So then the K has to be 0.013. Do you see that? Yeah. Okay. Okay, so then before we would have to sit there and use multiple equations to sit there and figure out what our K value was. So here, all you would have to do is plot the information. So you saw how fast that plotted? Piece of cake. So if you're doing it using, let me pull this up, let me pull up Google Docs. It's been a long, long day. And I have to get my weekly COVID test. I was exposed. sheets. Let me copy this data. Okay, so Google Sheets is going to behave exactly the same way. So you go to Insert. We're going to use Chart. So we want a scatter chart. So we're going to have our Y value is going to be our A, and then our X value is going to be our T. What was that? You said the lines wouldn't pop up? So it's not working on yours? Oh, I see. They're all at 4 because of the scale. So we have to change the scale. Not to remember how to change the scale. Oh, here we go. Let's see, what are we going to use as a spacing? Well, still the same problem, huh? Let's go. Point. Okay. So it doesn't work because it's too small? Is that what you're telling me? Let's see if we'll magnify it by 10. 10. We'll go A times 10. Uh-huh. Value? Okay, let's see. Max. Oh. And then go. What was that? Okay. Okay, so I'll have to figure out how it works with this.
I figured out how it works.
Okay. What do you recommend, Abel?
Delete the graph,
Okay.
and then from there, just select the original values,
Okay.
and then insert chart.
Okay.
And then for your x-axis, right, where it says like TS,
Yes.
change it to A instead.
Okay.
And then change your series to the times per second.
Okay.
And then you can scroll up to set it to the scatter plot.
And then
Oh
it
wait,
does
if
the
you set it,
let's see, hold on.
and then if you want the trend line, go to customize. Click series. And scroll down till you see trend lines. The thing I don't know is how to make it show the equation.
See. Not the label. Hold on. Okay, so but then the thing is that it gives us the value for, there has to be a way that we can get it so that it'll actually show us the other value. I mean, so that it will be y, because otherwise we have to switch the equation around to fit that model. But and so your slope is now not your slope is now not the slope of the k value. So
Yeah.
okay, so let me play with that. I'll figure it out for you guys. So how many of you guys have Excel? Do you guys all have Excel, or you don't? You don't own Excel? You can get it for free as a student. Yeah, it is the same thing as Google Sheets. Only thing, as you can see, it's a little more flexible. Yeah, so you can download it if you go to, you know how you go to your portal? Oh, you already have it downloaded? Okay. Yeah, so then just try plugging it into there. So, and then until then, I'll figure out how to do it on Google Sheets. So I know there's a way. Yes. I believe I made on the slide is a mistake. So, because it should be a zero order, because the data actually fits it pretty well, right? Like dead on. Let me see. What slide is that? 20, 40, 40 something, 51, 61. Boy, we've been moving. So 60, 61. Mm-hmm. Okay, so let's, yeah. So the K value is better with the, hold on. Okay. Well, so what we'll do is we'll take the log of this guy because it's the natural log of it. So it's ln the concentration of A. Okay. So equals ln this value. Okay, so now I have to fix the chart. C. What was that? It works with the natural log better fit. Okay, so then it's a first order reaction, not a. It's just, again, the R value. So we take a look at that R value. So typically what you would do, you plot both all of the possible points, and then you'll compare the two. Because usually you're not given the answer. Well, this one is giving us the answer. I just decided to ignore it. Okay, so our X value is here. And then our Y value is here. And so these two, that's ln concentration of A. This one. Should probably graph them independent of each other. Oh, yeah. Why do I have 4 points? Okay. Something is wrong. Y value for is 1.3. There's something wrong with the data point. Give me 1 second while I try to figure this out. This has been one day, one hell of a day. Things that usually work perfectly. Three data points. Let's see. Insert. T. This one. Okay, so I'll have to figure it out how to make it pretty again. So usually you're able to do both graphs on the same one, so. So, but you're right, the R value here is it's a little tighter than you have for this guy. So then in this case, then our K value is 0.0033 for that. So
So then we would have to take the market off.
yeah. So well, no. So normally what you would do is you don't, because they told us this was a first order reaction, right? I just, like I said, I ignore that. So normally what you would do is you would see the one that fits the best. So you go the first order, you go, I'm sorry, zero order, first order, second order. And then you see the one that fits the curve the best. Okay. So let me give you another example. So we take a look at the next data set. Okay, so determine the order of the equation from the following data. Okay. Let me pull up the data. And I am having a hard day with technology today. This is what happens when you get 3 hours of sleep. Okay, so here's the data. Things are not working out today. Ugh. And again, the rate constants are usually determined by experiment, right? So this is typically how you go about doing it. You plot the data after you get it. I didn't realize you're here. Really? Let me know when you guys got the data entered. Since the other thing is you want to download the Excel, because if you use the online version of it, it doesn't have all of the functionality. Ugh. Ugh.
R-squared value.
Yep. So you want the R-squared value that best fits the data.
And then, so for the first order, it's the natural log A. And for the second order, it's 1 over.
Mhm. That's right. This one worked out nicer. So much better on all programs. Okay, so let's see. Not want to work for me today. My programs keep crashing. 1 second. All my Excel, I mean, all my Microsoft stuff is crashing today. So. Come on. Okay, so this is the data that as entered. We want to take the first order. So that's going to be ln concentration of A T. And then we're also going to take the second one. ln, sorry, 1 over A T. Okay, so then we just put equal ln parentheses, select our value, those parentheses, hit return. So once we do that, we could just drag it down. In this case, same thing. We're going to put equal, and then this is going to be 1 over our value, and return, and then we're going to drag it down. Then we're going to plot all of our data. Okay. So we're going to add trend lines to everything. So we'll go ahead and hit trend line. First one. Oh, here's the data. We're going to have it display the equations, and then also the R value. Then I'm going to select this data point, and I'm going to add the trend line to that guy. Go down to more. Again, we're going to have it be linear. And then, so that was for a then I'm going to select this one here. Trend line, more. select display equations. Okay, so now we have all of our equations. Based upon the equations, which one has the best R value? The R squared value. Second order. Okay. So that means our second order is the one that best fits the data. So then that's going to be the one that we would go with. Okay, so it will be a second order reaction. Are you guys with me? You have that luck. Oh, the equations? Yeah. So all it is that the very first one is a natural log. So you always want to put equal when you're entering a function. Natural log is ln. Then you want to put parentheses. You select your value, close your parentheses. That's it. And then this guy is natural log. I mean, not natural log. It's 1 over our a value. So you just put equal 1 over a, that a value. And then all you do then is just take that corner and just drag it down, and it'll fill in, autofill in for you. You guys are doing the, are you having fun? Is that, are you having fun? You've gotten better. And you guys are checking the water to see. Okay. So then our K value would be what in this case? If it's a second order reaction. Okay. Okay, piece of cake. Okay, good. Okay, so let's go back to the lecture. Okay. So in this case, these are the how the values would look if we didn't make that adjustment. If we applied it the way it was. And plotted each one independently. Okay, so the next thing that I want to talk about is the collision theory. So the collision theory basically says that reactants must collide for them to react, right? And that's basically the case, right? You have to be able to get in contact with each other if you're going to have the reaction to occur. So I want you guys to think about it. Why doesn't every collision result in a reaction? That's right. So that's right. Okay. So that is correct. And so that aspect of kinetic energy, so that's going to be your activation energy, right? So the energy that's required for it, that threshold energy, as you mentioned, is your activation energy. And so you have to reach a certain threshold before you can actually get a reaction to occur. And as you said, it's also orientation. If it's not oriented right, it's not going to collide. Okay. And so here, this guy's oriented around, so you're not able to get a reaction. in this case, you have the right orientation. It reaches that threshold, so you're able to get a chemical reaction. Okay, so the dark blue slides are back, although they're not blue on yours. So the factors that are going to be involved in the collision theory is going to be the concentration, and that's going to deal with a lot with proximity, right? So the more stuff you have, the more probability that you have things going to be oriented in the right way, the more collisions you're going to get, right? Temperature, well, that's going to help us get to over that threshold energy, right? So as the temperature increases, that's going to affect that energy component. State, well, if it's only reacting on the surface, let's say we have a solid, then that's also going to affect the reaction kinetics. And the last one is a catalyst. Well, catalyst helps orient our substrate so we can make sure that our orientation is correct. Okay, so the activation energy is just basically the minimal amount of energy that is required to start a chemical reaction. It's that threshold, as Daniela was saying. So when we look at Arrhenius' equation, this is going to relate the temperature to the activation energy. So if we take a look at the temperature, so 1 over T, EA is the activation energy. So are they directly proportional or indirectly proportional? They're directly proportional to each other, right? So as temperature goes up, the energy is going to go up. Okay, and that kind of makes sense. Okay, so in this case, R is going to be a 8.314 joules per Kelvin moles. That should be a capital K. My bad. Okay, so this here just shows us that threshold energy. So this is the activation energy. So it's kind of like a chemical reaction is kind of like somebody's trying to push something over a hill, right? You got to get it up to the top before you can use, have it. What was that? That's right. Yeah. Okay. So this here's the activation energy. This is the change in enthalpy. And then this here is considered the transition state. That's the point where you go from not an active complex to an active. Okay. So, and also at that transitional state is considered to be where you're going to have your intermediate occur. So if we sit there, we think about it. If we raise the temperature on cooking food, our food cooks faster, right? So that is an example of that reaction going faster. So if we want to slow down the rate of food spoiling, we put it in a refrigerator, right? Because it slows down that chemical reaction that's happening with bacteria. And then if we want to slow reactions altogether, we put things in the freezer, right? Because that will slow those chemical reactions. So we sit there, you guys remember, did we do we didn't do it in this class. Did we do the glow sticks experiment with ice? Oh, okay. So got to do the glow stick experiment with you guys. So. Directly proportional. No, indirectly proportional means, so if you take a look, So you have EA over T, right? So if your equilibrium is let's say it's a function of time, I mean of temperature, right? But let's say we kept the equilibrium constant, right? So then if the activation energy goes up, what must the temperature must do? Are you sure? So if it's going to be kept, if this is going to be kept constant, if it's E over T, it's E over T, right? So let's say this is 1. If this is 1 right here, right? And we go from the activation energy being 50 to 100, and let's say, okay, you got it?
Yeah,
Yeah.
and then in the next slide, or the part that we're at,
Yeah.
it says, reaction rate. Does that mean
The rate will increase with temperature. That's right. Because the rate is going to be affected by the constant, right? So in this case, if we've kept the activation energy the same, we're not changing the activation energy. We're not doing anything to change the equation, right? We kept the activation energy constant, then temperature, as temperature increases, our K value should also increase. Think about that. Natural log minus the natural log. Because it's going to cause our reaction to speed up, right? So that K value should increase. So let's say, for instance, again, if we'll say that this guy is 1, right? So if we say the temperature is 20, then this value is going to be really small, right? And then the K value, which is the log of that, is going to actually get bigger. So is it because the natural log is the natural log, we have the minus, and then as the natural log gets smaller, because this guy's gonna get, sorry, smaller or bigger, right? As temperature goes up, no, this guy's gonna get smaller. Let me think about it. Let's put numbers in because that's the best way of showing it. Okay, so let's say we had 100 degrees here, right? And then so we go from 100 to 200, and we're gonna just say R is gonna be a constant, so we're not gonna worry about it. So we're just gonna say 1 over 200, 1 over 100 minus. Okay, put in those values, and then solve for K. Negative. And then we'll take the exponent. Okay, so here is going to equal 2.7. And then if we have 1 over 200, negative value, exponent. 1 over 100. And 2.71. 1 divided by 200. Good choice. Let's do 1,000 because the values are so close together. So. Okay, so here we know that this is going to be a constant, right? We're going to assume that we're going to make the assumption that the activation energy is just 1, right? Or we can say 8.2 314. Okay, so then that way this is just 1. So all we're looking at is temperature, right? Now temperature is affecting K. Okay, so then we want to solve for K, not ln K, right? So then we'll take the X. K is our constant. It is the rate constant, yes. It is the kinetic rate constant. Okay, so what we're doing is we're gonna have K is gonna be equal to E negative EA RT. Okay, so in other words, as if we make the assumption that this is going to be equal to 1, then we're going to have K is going to be equal to E over negative 1 over T. Okay, so let's say for kicks and giggles, we'll start off with T being 20. Okay. Okay, so then in that case, K is going to equal 9.95, right? So then if we say that K is 1,000, right? So we're going from 20 to 1,000. I mean T, not K. T is 1,000 or 2,000. Yeah, because that's what I think I wrote down here. Right. So 1 divided by 2,000, and then value. So then K is 0.9995, right? Okay. So as the temperature increases, K is going to increase, but it's doing it exponentially. So it's not going to be like, oh, bam, you know. So does that make sense? And that logistically, that makes sense, right? Because if a reaction, as temperature increases, things happen faster, right? So yeah, because let's say, like we were talking about food, right? So if I leave my food out on a hot summer day, right, it's going to go bad a lot faster than if I leave it out in the winter, right? That's right. Yeah. So if we adjust the reaction so that we are screwing up with the activation energy, yes. So then you'll have them being comparable. They both have to go up, right? Okay. So what I'm gonna have you guys do, we're gonna stop here and we'll pick it up on Monday. I thought we don't have that much more. It seems like there's a lot more, but a lot of it is just pictures, you know. So real cool. I mean, Wednesday. but I was gonna have them come anyway.